Hey everybody, today I'm going to be teaching about quantum numbers, which is the method that we use in today's model of physics to describe the orientation, size, and shape of orbitals around atoms. So let's get started. So there's three quantum numbers. We have n, known as the principal quantum number. We have L, known as the angular quantum number. And we have m, sometimes m subscript L, which is the magnetic quantum number. So, N, principal. This was actually introduced by Bohr when he was describing the shape, or not actually the shape, but the size of orbitals and their associated energies. So that was before this whole method of describing the orbitals of atoms is in Schrodinger's theory of quantum mechanics. But Bohr came up with N. Schrodinger just borrowed it because it's quite useful. So N, what N does is it describes the size of orbitals. So let's say we had a nucleus here. This would be like N equals 1. And this would be like N equals 2. So like you can just think of it as, yeah, two spaceships, one's in a small orbit, one's in a big orbit. This is N equals 1, this is N equals 2. It's a very classical way of thinking of it. A better way and a more advanced in physics way of thinking about it is the associated energies of the orbitals. Because in this, that was pretty bad glare on that. Well, anyway, in this instance, n equals 1 is actually a lower energy orbital than n equals 2. So you can just say a higher n is simply just means a higher energy orbital. Okay? But a bigger orbital works as well. You can think of it that way if you want. N is associated with the size of the orbital. So, what's the limit on n? I mean, how big can an orbit be? You know, how big can the orbit of an electron be around an atom or a nucleus? It's not really a limit, right? It can't be 0 because it's got to have some size. But these, by the way, all these numbers are integers. That's all of quantum mechanics is based around the fact that these things are integers, really. Okay, so n can equal 1, 2, 3, so on and so forth. Can't be like 2.5, but it can be any number from 1 to infinity, not 0. Any integer from 1 to infinity. So L, the angular quantum number, we got size. L describes the shape. And L, by the way, this is angular. Angular describes the shape. So like, for example, L can be 0 because it's more abstract than n. And the size of an orbital has to be some size, but the shape of an orbital, a 0 doesn't necessarily break any laws of physics. It just means it's a spherical distribution. So if I had like L, like here's my nucleus, if I had an L equals 0, I would have a spherical distribution around the nucleus. So if I went to any point around my nucleus and I said, hey, is my electron here? My likelihood of finding the electron there is just as good as if I went to anywhere else, is 0. You can think of it as it gives you no information about where the orbital is at if it's L equals 0. L equals 1 looks kind of like a teardrop and a teardrop. Let's move this L equals 1 down. Can you still see it? Yes. Teardrop and a teardrop. So if I go here on my L equals 1 nucleus and I ask, okay, is there an electron here? The likelihood is very small that there's going to be an electron there. Whereas if I went here or here, the likelihood is very large. So in this case, the classical sense of quantum mechanics of just thinking of them as little balls, in orbits around the nuclei kind of falls apart because it's like an orbit never does that. So, but anyway, it tells you the likelihood of an orbital being in these spots. L equals 2 happens to be this distribution. L equals 1 happens to be that distribution. L equals 2, I believe, is a clover. L equals 2 is a clover. But the point is, principal quantum number describes the size of my orbital. Angular quantum number describes the shape of my orbital. So what does magnetic quantum number do? Well, you got to remember these, well, we'll get to that. First, let's go over the rules of L. L can be 0, and then 1, 2, 3, all the way up to infinity? No. There's a limited number of shapes that you can have for an orbit, which is kind of weird to think about, but it's quantum mechanics. There's a quantifiable amount, meaning I can count to it on my fingers, of shapes you can have for a given n. So for a given size of orbital. And that happens to be, L needs to be greater than or equal to 0, but less than or equal to n. It has to be less than or equal to n. So it can equal n, it just can't be any larger. Let's make sure that's right. Oh, no, it can't equal n. Whoops. Okay, that's okay. I'll just cut that part out. So L, the principal quantum, the angular quantum number goes, it can equal 0, but it cannot equal n. So let's say that my principal quantum number was 3. L could be 0, 1, or 2. And that's all. And what that's saying is there's 3 different shapes I could have if my orbital was of size 3. You can kind of think of that way. So magnetic quantum number, what that quantifies is the orientation of, and actually I'm not going to erase that, I'll leave that. So that's the magnetic quantum number. And that quantifies the orientation of my orbitals. So you can think about it, these things are in 3D space, right? So if I have a given size, I pick a given shape for it, but like let's say this is my shape, here's my nucleus, and I have an L equals 1 orbital. I can be like that, or it can be oriented like that, or it can go into the board and out of the board. I mean, there's any number of ways that it could be facing because it's in 3 dimensions. So ML says that, okay, based on ML, this orbital is going to be facing a given way. So it will tell you if it's like this, or like that, right? So ML can go between minus L, and it can equal minus L. And L. So if L is 3, ML can go from minus 3, minus 2, minus 1, 0, 1, 2, 3, all the way to 3. And there's a quantifiable, I mean, there's only so many ways you can flip an orbital that's not repeating the same orbital. So that's why there's a limited number of MLs for a given orbital. So that's about it. Again, we have principal quantum number, angular quantum number, magnetic quantum number. And it's very handy to remember the rules that govern them. There's not really a pattern. We don't really have a mathematical formula to calculate how many M's are there for a given N and L. You just kind of have to do it by hand. But the theory is a work in progress. So anyway, thanks for watching, guys.